Welcome back, happy fabricators. So today we're going to be talking about the importance of using crush tubes in your fabrication projects. So today we're going to be talking about what a crush tube is, why it's so important, and how to properly execute it in your project. So let's get started. Okay, so what is a crush tube? So its most common application is going to be in tubing, whether that be you're fabricating a chassis or a roll cage or whatever that might be. Now, I know we're fabricators, so we have welders. So when we connect our tubing together, most often we're going to weld it together. But every once in a while, there's going to be the application where we need a removable joint or a joint that is serviceable for some reason or another. So we have to bolt it together. So what do you do then? You've consulted the professionals and carefully selected the tubing that you're using for your project to be the lightest possible, but still maintain the strength that's going to be needed for the job at hand. So then you examine the part that needs to be carefully fastened to your parent material, select a fastener, and drill an appropriate sized hole. You slap that guy in there and crank her down. And then this happens. So what just happened here? You tightened your hardware down to the manufacturer's specifications, but obviously we compromised our chassis or our base metal, whatever you're working with here. So what happened here is both these pieces are made from steel, your chunk of hardware and your base metal. And metal in general has two different ranges. One is called its elastic range and one is called its plastic range. So I'm going to see if I can explain this best with this extension spring here. So just for the sake of the example, we're going to say that the bolt failed instead of the metal underneath because it'll be a little easier to understand with this prop that we're using. So let's just say that the head of our bolt is here and the nut on the bolt is here. And when we tighten our nut up, we're essentially stretching that bolt out. We have a clamping force that's going up against our material. So our elastic range is the point at which we can tighten that bolt down and stretch it out, and if we loosen it back up, it will return to its previous form without being compromised. Now its plastic range is when we extend that spring too far, and then when we let go of it, we go beyond what is called the yield point, and it will not return. So you may say, well, just don't tighten the bolt down so much then. Well, that can also cause you problems as well. Believe it or not, fasteners and bolts have a specific designed amount of clamping force or pressure that they need to be tightened to be able to maintain the tensile strength that the factory specs them out at. That's why when you're assembling your car or whatever, your manual has torque specs for your hardware. So in most cases, a piece of hardware, or a bolt specifically, is meant to have a certain amount of clamping load or torque applied to it constantly to maintain its maximum tensile strength and longevity. So this clamping load is in the sweet spot, and in most cases that clamping load is right around 75% of the bolt's yield point. Now this is going to be different for different types of bolts and stuff, but you'll get the point. So your bolt's yield point is at the intersection of elasticity and plasticity, like we talked about earlier. So below the yield point is the point where you can loosen that bolt up and reuse it, and it's still going to maintain the properties and strengths that it was originally manufactured for or intended for. After you pass that yield point is the point where that bolt is going to plasticize and start stretching. So that's why, like on head bolts and stuff like that, sometimes you see a torque to yield and you cannot reuse those bolts on heads because they're torqued to that point where that metal has plasticized and started stretching to a point where it cannot return to a manufacturer's spec that would be able to be re-torqued down. So most of the time that torque spec is going to be right in the 75% range. So that means it's 75% of the amount of pressure that it's going to take before it starts plasticizing. And then once it starts to plasticize, you get your peak tensile strength, and then you'll eventually get a failure in your part or hardware or whatever reaches that point first. So I know this is kind of in depth, but I just wanted to explain how all this works and the importance of reaching this clamping load. So what happened on our piece earlier is we were trying to obtain this clamping load, and in the process of trying to obtain the clamping load for our piece of hardware, we exceeded our yield point on our substrate or our base material that we were bolting to. So the question is, so what do I do about it? The first option that most people go to is thicker materials. So as you see here, we have an 1/8 inch wall tube instead of a 1/16 inch wall tube. And in some cases, this is a great option. Your thicker wall is definitely going to be more impact resistant. It's going to have a higher yield strength because it's thicker, and it can do the job. But in some cases, maybe you're on a race chassis and you need that weight savings. But that's not always the case. Sometimes you have a larger bolt and the required clamping load still exceeds the yield point on your thicker material. And that, my friends, is where our crush tube shines. In utilizing a crush tube, we can still maintain our lightweight material that was spec'd out for our original application, drill our hole through, weld this guy in, and still achieve the manufacturer specs on our hardware that we're clamping to. So let me show you how this works. Okay, so the first thing we're going to do is we're going to take the piece of hardware that we've selected and determine its size. We have a 3/8 bolt here, and then we want to find a chunk of tubing that piece of hardware can slide into. Now sometimes you get lucky and you find something that fits fairly good, and sometimes you have to bore what you have out. But we just want that piece of hardware to be able to slide in there freely. Next, we're going to take and measure the distance of the tube or chassis that we're going to be bolting through and translate that measurement onto our crush tube. Next, we want to grind or machine a bevel onto both ends of our cut crush tube. Now the depth of this bevel is fairly critical, and so we want the bottom of our bevel to be on the inside of our tube. So it looks like I need to bevel this guy just a little bit more. Next, measure the outside diameter of your crush sleeve and drill a hole in the decided area on your tubing. Okay, so after we got our hole drilled, the next thing we want to do is take a countersink bit, if you have one, and we want to taper the inside of that hole just slightly. And what this is going to do is the combination of the taper on the tube and the taper in the hole is going to give you an area to fill with weld, and then when we go to resurface this and grind it off so that whatever we're bolting to it mounts up flush and our washer and nut can sit properly flat on the back side, you'll still have some meat in there left over. So we don't want that weld sitting on top. We want to bevel both of them if possible so that we get good penetration in that hole and we get the maximum strength out of it once we grind the weld off the top and the surface. So I installed the crush tube in the 16th inch wall tube here, and we also have our 1/8 inch wall tube. Now we're going to do a little experiment here. Both these pieces are roughly 19 inches long. I cut them to the same length, and they're right around 19 inches long. I set them on the scale, and this guy weighs right around 750 grams, and this guy weighs right around 1,500 grams, somewhere in there, give or take. So understandably so, it's twice the wall, twice the weight. We only added about 20 or 30 grams by adding that little crush tube in this 16th inch wall tube. So what we're going to do is we're going to bolt on these tabs to both these things, and we're going to torque them down to the factory specs for a 3/8 inch bolt. So best I could find, there's lots of different things, depends on what you look at, anywhere from 23 to 27 foot-pounds, depending on if you're using lubricant and if it's zinc coated and yada yada yada. So we're going to pump these both down to 25 foot-pounds and see what the difference in distortion is between the thick wall and the thin wall now that we have our crush tube in there. Okay, so we got the torque wrench out here, and we're going to set this guy to 25 foot-pounds. Should be somewhere in there. And then I'm going to torque these from the bolt side. I'm pretty sure that is the way you're supposed to go about it. Let me know in the comments if I'm wrong. First off, we're going to start with our 16th inch wall. So this is the thin wall tube with the crush tube installed in it. And there we are at 25 foot-pounds already. And now let's do our 1/8 inch wall. And there we are. Let's see what we got. Okay, so now that we got these guys bolted together and torqued down to their proper clamping force, our tabs are nice and solid on there, but we do have some deformation in one of them. And would you guess if it's the thinner or the thicker one? And it is the thicker one without the crush tube in it. So even though this is a thicker wall, it's hard to tell. Now I don't have a micrometer zooming exactly on this guy, but if you see the light, you can see the dimple around the washer there. If you look at it from the side profile, that washer is slightly sunken in below the material. So who's to say if that has reached its yield point? It definitely compromised the integrity of the walls. So especially if this was a chassis application, that would not be very good. But if you look at our 1/16 inch material, you can see the washer completely there. It's not recessed at all, and there is zero deformation in that tube. And that is why I really like this technique. It opens so many doors for you to be able to bolt on heavy duty things into lightweight situations, whether it be something structural like a roll cage or something like that, or chassis. Like I said, I've seen multiple occasions where people bolt all the way through a chassis and do not put any sort of crush tube in there, and is just not a very good solution. As that chassis or whatever it is getting put under stresses from the leverage of whatever you bolted on, eventually it's going to fatigue that material and eventually loosen that bolt up and then cause all kinds of issues for you. So make sure if you're using thin material and you're running a bolt through something, use a crush tube. So hopefully this technique is of some value to you guys. Like always, if you want to see more fabrication content, click one of the links that's going to pop up here. If you learned something new today, hit the like button, subscribe for future notifications, and go build something, guys. You know what? We're going to do a bonus thing here, and we're going to crank this puppy up to 50 foot-pounds. So this is our thin wall again with the crush tube, and we're going to take her up to 50 foot-pounds of torque. I don't think it moved at all. Nope, we did get just a little bit of deformation there, but that's twice the recommended clamping force right there. Oh, there's 50. And look at that, we squished it even more. I don't know if the camera's picking that up, but that washer is well below flush now, and that definitely compromised the wall integrity.